Thanks so much for being here. I thought it was actually going to be warmer when we accepted the invitation some months ago, but it's still we have a foot of snow on the ground in Baltimore. So in that regard, very nice. So I'm telling you today about, if you will, kind of a progress report in a new technique that my group has been developing for the last number of years. So my group generally does optical spectroscopy. I've spent the last 17, 18 years kind of trying to develop precision measurements where we look at interesting materials with at the level of linear response. So we'll measure things like the optical conductivity of materials, superconductors, topological systems, things like this. Or we look at the magnetic susceptibility. We'll look at, say, spin systems where we couple to the material through magnetic dipole interaction. So what I'm going to tell you about today is kind of, if you will, next generation experiments where we use multiple pulses of terahertz radiation, more intense, where we can induce nonlinear effects in materials. It's complicated, but there's good reason for doing something. We should have good reason for doing something complicated, and that's because we can get information that we can't get out at the level of linear response. Okay, so that's what the talk is today. I'll tell you a little bit about the background of it, and then give you some examples of a variety of different things that we've done, but mostly centered in the area of correlated metals, so interacting metals in various ways. The talk doesn't have basically anything to do with machine learning, but I would say that particularly when you're calculating some of these nonlinear response functions, it really is at the complexity frontier of what's possible with numerics. And so in this regard, I encourage computationally minded people to think about these things and maybe there are applications for machine learning algorithms. Okay, what's going on? No, it doesn't.
Look on the PowerPoint.
What's that?
The PowerPoint. I think you're on the Zoom. Yeah.
Oh, there we go. Good. So before I get into it, let me thank the various people that make it possible. A number of excellent postdocs and students over the years. I want to point out in particular two students. Current student Will Liang, who's heading the experiments now, particularly on the Coherent superconductors, and a former student, Deepajan Chowdhury, who went on from me to a postdoc at University of Illinois and is currently on the job market. But it was really Deepajan who set all of this up, and he is the one that has been primarily responsible for its success. What's the phone?
Just move it on.
Oh, I see. There's this. Huh?
It's still sharing. Yeah.
Very good. So maybe just some general remarks. So first, optical nonlinearity is, of course, an old subject. Any physical system has nonlinearities. We typically, as a first pass in trying to understand a physical system, like to try to understand in terms of its linear response. Linear response is familiar to us. Hooke's law, Ohm's law, all of these things are examples of linear response. We like linear response because it's the simplest. It's very powerful. There are a lot of kind of well-characterized various identities that we can use to make sense of the data, some rules, these kinds of things. But nonlinearities are, they can be a source of complication, but they can also be a source of information in physical systems. And generically, we try to think that we might take some physical system and expand, let's say, a time-dependent polarization in functions of the incoming electric field. The first term is, of course, the linear response, but then there are higher order terms, and there are various symmetry considerations that determine whether some of these are allowed or not. There are various different kinds of processes. Maybe I'll stand back here so people can see a little bit better. There are various kinds of processes that people speak of in the context of optical nonlinearity, things like second harmonic generation, 2 photons come in and 1 comes out at double the frequency. Third harmonic generation, just an extension of that, but with 3 photons. This is a Chi-2 process. Difference frequency generation, 1 photon comes in, and then, if you will, 2 come out. Always we conserve energy in this fashion. The one which is going to be principally interesting and useful for us in this context is something that we're going to call 4-way mixing, where we consider 2 positive frequencies and a negative frequency, and then a 4th frequency emitted. An important point at the beginning of all of this is we need to have a slightly different, when we think about nonlinear response, we need to have a slightly different way of thinking about interaction of light with materials than we do with linear response. So it's very useful language very often if we're thinking about doing a linear response style experiment, when we think about optical absorption, right? You'll use language like the photon, started here, passed through material and was absorbed and then didn't arrive at the detector. So that kind of language is not useful for us when we think about nonlinear response, or not particularly useful. What we want to think about is we're taking a physical system, we are driving it in some particular fashion. This driven charge is itself a source of radiation, and that source of radiation re-radiates, and then we detect the resulting re-radiated signal. That re-radiated signal, let's say, you can apply that to linear response. It could be, for instance, 180 degrees out of phase with the driving field, and that's absorption in that context. But we need to have a kind of slightly different conception of what we're thinking about here. So I'll give you my conclusions in the beginning. I'm going to tell you about this particular technique here, 2D coherent spectroscopy, and I hope to convince you that it's a nonlinear Chi3 technique, and it has tremendous potential for various kinds of quantum materials, spin systems with fractionalization, electronic glasses, correlated metals, kind of thing. I'm going to give you in particular new information about nonlinearities interacting metals, and what I will show you is that we can measure the relaxation from different modes versus the conventional one of Fermi surface perturbations. So in a conventional optical experiment, or even, if you will, in a kind of a quasi-DC experiment, we think about taking a Fermi surface and shifting it, and then watching it relax back to equilibrium. But with lots of more pulses, if you will, we can distort the Fermi surface in various fashions and watch it relax. And these kind of high-order angular momentum modes encode different information about interactions that you can't get at the linear response. And then I'll give you some specific examples of all this. Okay, so 2D terahertz. Okay, so first I just give you a kind of a very cartoon version of what's going on. So we're going to imagine doing an experiment with two pulses. We'll call them A and B. And the general protocol we're going to have is that we're going to imagine driving the system with A, driving the system with B. We can drive it with A and B together, or we can drive it with A and B separately. And then we're going to look at the difference spectrum. And the difference spectrum is kind of by definition the nonlinearity, right? So we're going to generally plot the nonlinear response in this fashion, right? So if the system was purely harmonic, you would do the experiment with A, with B, A and B together, subtract, and you get 0. But there are going to be small residuals, and that's the nonlinearity. So imagine a situation where I have two weakly nonlinear oscillators. You could imagine them, let's say, charged pendula in this fashion, and I can drive them. And I'm going to plot as a function of the pump and probe directions. I'm going to, as a pump frequency and a probe frequency, I'm going to plot the spectral nonlinear response, let's say, out of the page in this way. And if I had these two weakly nonlinear oscillators that were uncoupled from each other, this is what I would get, something like that at the cartoon level. Right? So if I pump at the oscillator's near its frequency, and then I probe later at the frequency, I can tell I've already pumped it. Whereas if I pump at the wrong frequency and probe it, then I won't get anything. Very roughly speaking, the projection into the probe frequency direction, that looks like the linear response. Now, imagine a situation where I take those two oscillators and I couple them weakly together. Now, what would happen in the linear response? Well, in the linear response, I might imagine the oscillators would shift slightly in frequency. They might broaden. They could get asymmetric. If I had a good enough theory, I could make some story out of what was that particular thing that happened. But very often, I don't have good enough theory. At the level of the nonlinear response, though, it's not a matter of having good enough theory. I get off-diagonal peaks where I didn't have them before. Right? So in this, at some level, it's as simple as I can reach in and I can shake the green oscillator and make the red one move. And so that's the basic idea, right? So there's, of course, lots of complexity that comes from it, but that's the basic idea. We could imagine taking, that's a system where I would have, say, two oscillators, which are weakly coupled together, but I could imagine a situation, let's say, where I have many oscillators, and that they are all individually, perhaps very well, they have long lifetimes, but they're uncoupled together, and it gives a frequency axis, which is congested like this. The projection, again, was a linear response. I would get this big blob. Each of these oscillators might be very long-lived, but I can't tell at the level of linear response because they're all just sitting on top of each other. But I could imagine taking this anti-diagonal cut in this fashion, and an anti-diagonal cut would reveal the inverse lifetime. Okay? So we're going to be doing a number of different experiments like this. Now, the way the experiments are done is with, I won't get into the details, but it's done with ultra-fast amplified laser, various kinds of beam splitters. You don't need to worry about a lot of the details, but I would just say that the lasers propagate around the table, and they come to these lithium niobate crystals, which are here and there. And through a particular, another nonlinear process, they make terahertz light pulses and are brought together pass through a sample in this fashion. We can measure them in the laboratory flame. We can delay the relative delay between them. We can turn pulses on and off. We can exploit their frequency dependence, etc. Okay. That's what data looks like. So that is, as I mentioned, that's A, that's B, that's A and B together, and that's the difference. And so that's a nonlinear response. You could really just imagine, this is in the time domain, but you could just imagine, two pond ripples crossing in front of on top of each other on a pond, and very often you can see that there's a small nonlinearity in the wave equation for waves on the surface of water, and there's a little bit of a ripple left behind after they pass, and that's exactly what we're looking for. Okay, all right. So what can we learn? So I want to give a number of different very quick examples before I kind of get into the meat of it, which is going to be mostly about metals. So this is an experiment on ytterbium. This ferrite here, it's a canted anti-ferromagnet. It has two different ferro and anti-ferro modes. It's a ferrimagnet, actually, the system, that are at frequencies that are something of order about 0.3 terahertz and half a terahertz. That's what data looks like here. So interpulse delay and some detection signal field. Now, one of the things in nonlinear response, in linear response, if I have some excited state, there's generally just one way I can excite it. A photon will drive that particular excited state. If I have a nonlinear response, and even just a ground state and excited state, there are generally many ways that I might be able to get to a particular excited state. And so that's one of the powers of the technique, that we can exploit different pathways for coming to the same particular excited state. And those different pathways can show interference phenomena. And so it's kind of complicated, and I don't want to get into the main details of it, but that is one of the reasons why we plot this 2D plot like this. It's a two-dimensional spectrum, again, excitation frequency and the probe frequency here. We have two pulses, and we use this, if you will, frequency vector scheme to find myself. That works. Okay, I'll move the stand here. That's much better. Good. So we use this frequency vector scheme to denote these different places in the two-dimensional plot and the different kinds of information they encode. So we would have, for instance, a signal down here that is negative frequency of one of the pump, and then two positive frequencies of the probe, which puts a contribution right here that we label with R. That's the rephasing response in, if you're familiar with things like spin echo or photon echo, that's the particular contribution that gives you a photon echo or a spin echo signal. Okay, it's a kind of a perturbative scheme of spin echo, but it's the same thing. That is a response up there, which is, we call the 2Q, and for this system, which is a magnon system, it corresponds to an excited state with two magnons in it. So it's kind of gives you, if you will, analogous and complementary information to two-magnon Raman. But in two-magnon Raman, you excite zone boundary magnons, and these are zone center. This is a response here, which is going to be particularly important for our looking at metals, where we imagine that we, if you will, excite the system with a positive power of omega, negative power of omega, and then positive power omega. This guy right here, E star E, that looks like an intensity. And so this particular response here is called the pump probe response. And so it kind of, to get a cartoon feeling of it, it's kind of as if the system has absorbed a photon, right? E star E, that's an intensity. And then the system is in a non-equilibrium situation, and then you're looking at the system afterwards as it's evolving. And that's going to be particularly important for us when we think about metals. Okay, then there are Chi2 responses that you could also take a look at. We're doing a lot of different things with this. My original motivation for this is looking at spin systems. And so we have this theoretical proposal of some years ago, still we haven't gotten this to work yet, but I think this is where one of the real powers of the technique is going to be, is looking at spin systems which have fractionalization. So we had a particular proposal here for the simplest model system with fractionalization, a ferromagnetic icing chain in transverse magnetic field. And you recall the picture that I gave you of the pendula, where there were many pendula that were kind of congesting a frequency axis. Well, it's a very, very similar situation. If I have a spin-on continuum, let's say, in a nominal spin liquid or a 1D chain, which has fractionalization, I have a congested spectrum, because there are many ways that I can satisfy energy and momentum. You get a proposal here about how you can get sharp spectroscopic signatures from fractionalized spin systems. That's theoretical, but what we've done experimentally is looked at a variety of different things. So we looked at phosphorus doped silicon, one of my favorite old systems on the insulating side of the metal insulator transition. So it's an early example of a quantum phase transition. And what was found here was you have these very broad spectra. It's a disordered system, a random ensemble of phosphorus interacting with each other. Again, a three-dimensional metal insulator transition. And what we found was that the energy relaxation rates go linear in frequency with a coefficient very close to 1. And in homage to Anderson's old notion of the Fermi glass, but here a linear relaxation rate, a relaxation rate which goes linear in frequency with a coefficient close to 1. We refer to this as a marginal Fermi glass, and this was published some years ago. We've been doing work with looking at collective modes in superconductors. And so there's been a lot of work, as you may know, about people looking at the amplitude mode in conventional superconductors, the so-called Higgs mode in superconductors. I prefer the old school language amplitude mode, but 2D terahertz provides a particularly diagnostic way of looking at some of this particular spectral signatures, and in particular distinguishing the amplitude mode from its almost degenerate continuum of quasi-particle excitations, which go at 2 delta. And I'm not going into the details of this, but you can just, perhaps be kind of interested in how these, again, two-dimensional plots are rendered and the different contributions that we can make out that correspond to different physical processes. Okay. Yeah. Okay, so I'm going to tell you about metals first, but maybe before I do that, I can just pause for a second and, I've kind of set the stage at this point, and people might have some questions on how does the technique work.
Yeah. Peter, could you quickly explain how it distinguishes the amplitude modes from the quasi-particle excitations?
Okay, maybe we should talk about this. So, the way it does it, we heavily rely on the kind of a diagrammatic. We worked very closely with people like Laura Manfato, who were able to show through diagrammatics that particular rephasing response, when you come in with kind of two strong probe pulses, is particularly sensitive to that for a particular reason that I could get into, but it probably will absorb most of our attention for the rest of this time. Yeah. But let's talk about it. Yeah, I'm happy to show you. Yeah, I mean, one of the things that comes out in a very model-independent way is what resonances we see. We change the temperature, we use a narrowband pulse, and the amplitude mode comes into resonance with the driving field. And how it comes into resonance and how many times it comes into resonance as you make, you can have, the amplitude mode is when the driving frequency hits 2 delta, but you can use 1 photon to get to 2 delta, 2 photons to get to 2 delta, 3 photons to get to 2 delta. And so that's a kind of level of complexity and richness that you don't have in normal linear response. In normal linear response, you got 1 photon, and if you're going to hit a resonance, it better have 2 delta. But in this fashion, we have the possibility of 0, 1, 2, or 3 photons hitting 2 delta. And that gives you a lot of extra information, and you can, with modeling, figure this out. Okay, good. So let's talk a little bit about metals then. So now we know that for the case of most metals, that maybe it's a kind of remarkable fact of nature that in most metals, despite the fact that the Baer-Coulomb interaction is not small and it's not short range, nevertheless, electronic system, we heard a little bit about this yesterday, electronic system organizes itself to render itself weakly interacting as long as the interactions are not too strong. Right? So this is canonized in the form of the Fermi liquid theory. There are other material systems, metals, which don't follow this paradigm of a weakly interacting at low energies Fermi liquid system. Right? And so the most famous of this is the cuprate superconductors, which famously show this so-called Planckian dissipation, where the scattering rate of the system goes like temperature itself with a coefficient very close to 1. And this was first inferred in this old paper of Fiori et al. In 1987, resistivity versus temperature. This is in lanthanum, strontium, copper oxide, which is going basically linear in temperature all the way up basically to the melting temperature of lanthanum, strontium, copper oxide. One of the famous aspects of this is that it just sails straight through the inferred mean free path, just sails straight through the lattice constant of about 4 angstroms of this system. And so you can come up with models which have linear and T resistivity over some range in temperature. And one of the real mysteries here, and I think challenges to understand, is just how this linear in temperature is given over such a broad range of temperature, where, if you will, different mechanisms, all of which can give you linear T, if you will, kind of smoothly pass the baton from regime to regime as you go higher and higher in temperature. There have been various hypotheses about this can happen, and one of the notions is that you have a fundamental bound, which is kVt divided by Planck's constant, and there are various scattering mechanisms which, if you will, saturate this bound, can't scatter any more than this bound, and so this is one way that you kind of get this notable universality over such a large. So this is the resistivity, some old data. This is some data from my group here, where we're looking at, this is a plot of the optical conductivity as a function of frequency. This is for a slightly overdosed sample. And so this is the optical conductivity. The DC resistivity is the inverse of the zero frequency point here. But this kind of Lorentzian form gives us a direct eye into what the actual scattering rate is, independent of any of the things that you would usually need to pull out the scattering rate, like density or mass, if you will, right? So it's just the width of these Lorentzians. And then this is a plot here of that rate as a function of temperature. Again, linear in T over, this is over only up to 100 Kelvin, but you get the basic idea. Just kind of keep on here with a coefficient close to 1. Now, this conductivity here, what it allows us to get, what it is formally, is the rate that current decays in the system. So even independent of a quasi-particle description, the width of the Drude peak is the rate that current decays in the system. If I get a current moving and I, let's say, take the electric field off, it will slow down after a period of time, and it's this width is, just by very simple considerations, is the rate of current dissipation. If the system has enough isotropy, we can relate the rate that current leaves the electronic system to the rate that momentum is dissipated. And so very often you'll see me write these transport relaxation rates as momentum relaxation rates. Okay, and so that's how it's indicated there in the plot. Now, let me tell you first something you know, and then perhaps something that you don't. So kind of a time domain version of doing such an optical conductivity experiment. When we do our actual optical conductivity experiment, we're using an alternating field, and we're taking the charge, and we're kind of sloshing it back and forth and looking at the in and the out of phase motions. A time domain version of that would be if I took a Fermi surface like this, and I did something, let's say, to displace it. This is maybe the kind of cartoon version that you can see in the elementary Cattell book. And then I would let it relax over some period of time, and the time scale that it comes back to the origin, that is this Drude relaxation rate, and it's the rate, again, that momentum leaves for an isotropic Fermi surface. Momentum leaves the electronic system. That state which the Fermi surface has shifted is a state of finite momentum. That's a state of zero momentum. Momentum's got to leave the electronic system, and it can leave the electronic system through coupling to phonons. It can couple to impurity scattering, and not for a simple Fermi surface, but if I have more complicated electron-electron interactions of Umklapp scattering, electron-electron interactions can take momentum from the electronic system. Okay? But that's not the only possibility, and in particular, when we have these nonlinear responses, we can imagine taking a physical system and perhaps using multiple pulses and driving it in such a fashion. And you can imagine, for instance, using 2 pulses, and if you will, taking the Fermi surface and rattling it back and forth, and, if you will, leaving the Fermi surface in this kind of regime here, where you've taken the Fermi surface, if you will, and left charges on the left and the right sides high. You might have done nothing here, and you could, this is a different distortion. This is not a state which has finite momentum, but it is a state with finite energy. So we might take a state like that, and we could, in fact, watch it relax as a period of time. Now, if I look, this would be the driving field here, E cosine squared theta, which I can turn like this, and you can see that there's 2 parts to this. One is a constant part, and one is a cosine 2 theta. And so that distortion that I referred to, I can actually break it down into 2 irreducible representations of, I'm sorry, I'm skipping ahead. Let me go forward one, and then I'll go back a little bit out of order. In I could imagine it taking a system, and I excite it here and excite it there, and I can decompose that into 2 different deformations of the Fermi surface, one of which corresponds to exciting the Fermi surface everywhere around. And the other one corresponds, if you will, to exciting it here and there and de-exciting it there and there. And so this deformation can be written as a superposition of 2, one of which is a uniformly excited system. And you could ask, how does the energy, or how is that deformation going to heal itself? And it can heal itself only through energy leaving the physical system. So momentum is not relevant. Momentum loss is not relevant, but energy loss is relevant. right? So how does energy leave an electronic system? Well, impurities don't matter because they're generally completely elastic. Electron-electron interactions don't matter. Two electrons can scatter off of each other, but they just exchange momentum, let's say, and they leave the energy still in the electronic system. It's just acoustic phonons, low energies, that are the only source to take energy out of the electronic system and put it into some kind of battle. This one here, this what we might call B1G or quadrupolar, is another deformation of the Fermi surface that doesn't require energy loss and doesn't require momentum loss, and it's something we're after here. What I'm going to be mostly telling you about is this guy and our applications of this technique to measuring energy relaxation rate in a few different physical systems. Let me just go one slide because I went a little bit out of order. This is kind of fits into a general perspective where you can imagine using multiple pulses and deforming the Fermi surface in various fashions. There's a lot of old school, particularly Russian literature from the 60s, where they talk about how to decompose the transport equations into these high angular momentum states, and it's something that we're after now. Right? So these are kind of the ones which are more intuitive to what you might be looking at. Some of these guys here are long-lived due to various conservation laws, and then we're interested through using multiple pulses and inducing these higher order angular momentum states of which there are interesting predictions. Okay, now let me say a few things, and then I'll show you some data. The energy relaxation rates in cuprates, and for that matter, for other materials like it, generally are believed to have a functional form that looks something like this: energy relaxation versus temperature here. At the lowest temperatures, one would expect something like T to the third energy relaxation. And again, this is electrons that are coupling to acoustic phonons. You go to some particular temperature, and then the energy relaxation rate starts coming down as you come into the elastic phonon regime. So one of the things that we can learn from this is energy relaxation rates, right? So we can learn something, if you will, about electron-phonon coupling. But the other thing we can learn is the range in which we cross over from electron loss from phonons to what this elastic phonon regime is. It's a lot more obvious here. You can find similar information, let's say, in looking at a resistivity experiment, where you cross to a linear and T regime, where that's the quasi-elastic regime, where the scattering rates go linear in temperature. But that's a much more subtle thing to find. Here, we can just look for where we might find a peak in temperature. So this would be the regime where you get linear NT resistivity. So let me show you now, maybe I'll go through that and just give you some examples of what we're actually doing with. So recently, a paper came out in PRL where we were looking at strontium ruthenate. You're kind of maybe used to looking at some data that looks like this now. This is the time domain data, tau versus T. This is its Fourier transform. And there's this streak here, which I already told you was the pump probe response. And we can look at the data here, let's say different slices, to give us the energy relaxation rate at different frequencies. Very often what we're going to like to do, instead of looking at the full 2D plot, we're going to look at, we're going to take, if you will, 1D scans, because it's goes a lot faster and gives us similar information very often. And that's what data looks like here. This is the nonlinear response as a function of time, and there are a number of different relaxation rates here. But the thing that I want to emphasize is the fastest one. This is momentum and energy relaxation rates in strontium titanate. The momentum relaxation rates, there are two different contributions to the conductivity. And this is the energy relaxation rate down here at very, very low temperature, at very much, you can see factors of 10 or 15 below the other ones. So energy relaxation is much, much, much slower than momentum relaxation. And, just on the face of it, we might expect this to be the case, that many different processes contribute to momentum relaxation, but only coupling to acoustic phonons are going to remove energy from the electronic system. And so from this dependence down here, we can pull out the electron-phonon coupling constant. It's a particularly crisp way of getting it, right? Because we don't see all of the other scattering channels that are all on top of each other and have to decide, is this electron-electron, is that electron-magnon, et cetera. This is just electron-phonon. That gives us this quite modest value for the electron-phonon coupling constant. And then as it turns out, we can use that to predict the high temperature regime to high accuracy, where this is going, the resistivity is going linear in temperature, and that works quite well.
So it's not electron magnon. gathering.
Look at-
Anti-ferromagnet, right?
Strontium
Is it?
ruthenate is not, is kind of close to being a ferromagnetic phase, but there's I mean, the neutron scattering is actually unclear as to what's going on. It's an important point.
It's not a high TC cell.
It's not a IGC. No. It's actually an important point, and literature has been interpreted that you can have, let's say, electrons coupling to all of the different bosonic baths that you might imagine in the system. I'm not sure that I believe this is a perspective where the electrons could kind of be at a hotter temperature than the magnons, which are themselves made out of the same electrons. So I don't think this has been dealt with the proper rigor of literature. I think that what makes sense is that electrons ultimately energy ends up in the system with the largest heat capacity, and that is by far is the phonons. There's an interesting point that's associated with this. Let me show you two.
But it was ordered, then it's also, the magnons also have a large heat capacity.
Yeah, but the magnons themselves are made out of the electrons.
Well,
So can we think that
those are collective modes.
Yes, I think Peter is right. I mean, unless you have some sort of a way to split this electronic system into two pieces and say, this is conduction electrons and these are, local moments, and then you are talking about energy transfer from conducting part, the local moment part, then you can
let's
do
come
that.
back to it. I want to finish up in the chairman is standing. So let me just show you maybe two quick things. One on doped strontium titanate. Doped strontium titanate is famously the lowest density superconductor that we have, and quite interestingly, it shows T-squared resistivity down to very, very low doping levels. So you have a tiny little Fermi surface in the center of the Brillouin zone, T-squared resistivity, and it's unclear how you can get that because the Fermi surface is so small that it can't. There's one band occupied, and the Fermi surface is so small it can't engage in Umklapp scattering, and so there's been various proposals that perhaps strontium titanate is famous for its unconventional lattice dynamics, that maybe, let's just call them strange phonons, are giving you T-squared resistivity. And one way that you could get T-squared resistivity from phonons would be to be in the regime where you would have linear in T resistivity, but it's two phonon scattering, T times T. And so this would be in a regime where you would have basically elastic scattering off of phonons. And this would be quite apparent in our energy relaxation rate. And let me just show that we actually, this is the momentum relaxation rates, and the energy relaxation rates are down here, an increasing function of temperature, and so not in the quasi-elastic regime. Let me go, we have interesting work that we've done in cadmium arsenide, which is a soft metal, looking at a particular itinerant ferromagnet, which also shows interesting dependence, and I would just kind of end with just showing the cuprate work. So we've done a lot of, this is the only part which is unpublished in the data I'm showing you here. Doing 2D spectroscopy on the cuprates over a large doping range. This is these kind of pump probe plots that I'm showing you, the nonlinear signal as a function of the pump delay time. And one can again pull out the energy relaxation rate from each of these and compare this to the momentum relaxation rate. And in all cases, you find that you're in a regime which is much where the energy relaxation rate is much smaller than the momentum relaxation rate. And you're coupling to the particular bath, which is pulling off energy, whether it's acoustic phonons, magnons in some particular fashion, is not in the quasi-elastic regime. So we're back to having, if you will, a puzzle with linear and T resistivity. We're still having a puzzle with linear and T resistivity in the cuprates, where some coupling to a bosonic degrees of freedom, which are themselves kind of excited at such high energies that they're quasi-elastic, is not going to be a mechanism for explaining cuprate circuit. And I think I will just finish there. You've seen the conclusions already, and so I'm happy to take questions in the meantime.
I think we have time for one question.
So in the cuprate, the pumper data, it looks like there's some coherent mode to the oscillation.
You get here
Yeah, it looks like there's
at early times.
Yeah.
Yeah, so that's an artifact from when the two pulses are on top of each other. Maybe I just, as we're just setting up, I would just address this other issue here. So I think that there's kind of ample opportunity here for people looking at,
Either way, yeah.
Do you have your own clicker or do you want?
I have my own.
trying to understand how these energy relaxation processes work. And it's not clear to me that this is a self